Welcome back to G Fun Facts Online, the podcast that dives deep into the wonders of our universe. Today, we're turning our gaze to the heart of our solar system, our very own star, the sun. Now, we all know the sun gives us light and warmth, life itself, right? But this fiery giant is far from a calm, steady beacon. It's a dynamic, often tempestuous powerhouse, constantly blasting out a stream of charged particles called the solar wind. And sometimes, it unleashes even more potent bursts, solar energetic particles, or SEPs for short. These SEPs are a bit like tiny, superfast bullets, and they can wreak havoc on our technology, both in space and here on Earth, not to mention posing a risk to astronauts. So how do we study these solar tantrums? Enter NASA's Parker Solar Probe, a mission so audacious, it's literally flying into the sun's atmosphere. Launched in 2018, PSP is on a daring journey to get closer to the sun than any spacecraft ever before, all to unravel its mysteries, especially how these high-speed particles get accelerated to such incredible energies. Fasten your seatbelts, because we're about to get up close and personal with our star. One of the Parker Solar Probe's biggest jobs is to figure out exactly what kicks these energetic particles into high gear, and how they travel through space. To do this, PSP isn't just observing from a safe distance. Oh no, it's flying directly through the solar corona, that's the sun's super-hot outer atmosphere. This is giving us first-hand data, measurements taken right in the thick of it, and it's completely changing how we understand these SEP events. Imagine the conditions. PSP has already made tons of close flybys, surviving mind-boggling heat and radiation to send back priceless information. And get this, on December 24, 2024, this incredible spacecraft made its closest approach yet, zipping just 3.8 million miles from the sun's surface. That might sound like a lot, but in cosmic terms, it's practically skimming the surface, and it was moving at a staggering 430,000 miles per hour. That's fast enough to go from New York to Los Angeles in about 25 seconds. So where do these solar energetic particles actually come from? Well, scientists have long linked them to two main types of solar fireworks. Solar flares, which are these intense, sudden bursts of radiation, and coronal mass ejections, or CMEs. Think of CMEs as colossal eruptions of plasma and magnetic fields from the sun, hurling billions of tons of material into space. Both flares and CMEs are powerful enough to accelerate particles to nearly the speed of light. Parker Solar Probe's keen eyes, or rather its sophisticated instruments, are helping scientists pinpoint whether particles are getting their boost primarily from flares or from the shock waves driven by these massive CMEs. It's like being a detective at the scene of a cosmic crime, figuring out the exact weapon used. All right, let's dive into some of the mind-blowing discoveries Parker Solar Probe has already made. This is where it gets really exciting. First up, the probe's IS instrument suite. That's Integrated Science Investigation of the Sun, and yes, the O is a sun symbol. Cool, right? Has found that small, energetic particle events are happening way more often than we ever thought. Even when the sun is in its quiet phase, its solar minimum, these little bursts are popping off. Scientists think these small events might be constantly trickling energetic particles into the inner solar system. These particles could then act as seed populations, like a starter kit, ready to be accelerated to even higher energies by the bigger players, like CMEs. Next, a really groundbreaking discovery, particularly highlighted by research from the Southwest Research Institute. Using PSP data, scientists found strong evidence that a process called magnetic reconnection, happening close to the sun, is a super effective particle accelerator, especially for protons. Parker's solar probe flew through something called the heliospheric current sheet. Imagine a giant, warped surface rippling out from the sun, where its magnetic field flips polarity. In this zone, PSP saw clear signs of magnetic reconnection, like magnetic islands merging and jets of plasma shooting out. And crucially, these events were directly tied to protons being accelerated to energies around 400 keV. This is a huge piece of the puzzle, offering a new way to understand how the solar wind itself gets energized, and how those explosive flares and CMEs manage to accelerate particles so effectively. Now let's talk about those CMEs. Parker's solar probe has literally flown through multiple coronal mass ejections and their associated shock waves. This is like having a storm chaser right inside the tornado, giving us unparalleled detail. One fascinating event on August 27, 2022, showed a three-stage particle acceleration process. The first burst of SEPs was linked to a fast CME as it traveled out to about 2.85 solar radii. Then, a second boost happened when this fast CME slammed into a slower CME that had been ejected earlier, way out at around 40 solar radii. This collision was so energetic it was accompanied by an intense interplanetary Type II radio burst. Basically, the sun was screaming on the radio waves. The third stage involved particles energized as the CME's shock wave passed by Parker's solar probe itself, further out at about 0.38 astronomical units. What's really interesting is that the particles in the second and third stages had harder spectra, meaning they had higher average energies. This could be because the shock from the CME collision was stronger, or because the earlier CME had already prepped a richer supply of seed particles. Then there's the injection problem. How do particles from the relatively calm, thermal solar wind get that initial kick to become CEPs in the first place? Data from a super-fast CME-driven shock, moving over 2,500 kilometers per second, observed on March 13, 2023, when PSP was incredibly close, about 0.23 astronomical units from the sun, shed new light. The observation showed that the accelerated particles came directly from the thermal solar wind, not from some pre-existing, slightly more energetic population. The rapid spike in energetic particle intensity also suggested they were efficiently trapped near the shock by magnetic waves, helping them gain energy. And it's not just about shocks. Another event on March 2, 2022, saw PSP fly through the side of a CME at about 0.2 astronomical units. Here, the energetic particle fluxes were highest inside times the CME structure itself. This points to local particle acceleration and confinement happening right within the CME's tangled magnetic fields and flux rope. So the CME itself acts like a particle accelerator and storage unit, building up populations of energetic particles that can then be fed into other acceleration processes further out. Parker's solar probe has also revealed that even when CEP events come from the same active region on the Sun, one right after the other, their composition can be wildly different. For instance, the ratio of helium to hydrogen can vary dramatically. Because PSP is so close to the Sun, these measurements aren't muddled by the long journey through space, giving us a clearer picture of the acceleration mechanisms and the conditions right at the source. We also have to mention coronal structures and the mysterious switchbacks. PSP has given us stunningly detailed views of CMEs and other structures. And it discovered these bizarre magnetic switchbacks, S-shaped kinks in the Sun's magnetic field lines. While we think these are mainly related to how the solar wind itself gets accelerated, these structures, and the general turbulence in the young solar wind, might also play a role in how energetic particles are transported, and maybe even get an extra energy boost. The IS data suggests that switchbacks could actually bend the paths of CEPs. Finally, even in its early orbits, PSP detected energetic particle boosts linked to what are called stream interaction regions, or SIRs. This is where faster-moving solar wind catches up to and plows into slower wind. The long duration of these particle enhancements suggests particles are streaming pretty efficiently along the magnetic field lines, and the buildup of these particles indicates that suprathermal populations, those just above thermal energies, get enhanced near these interaction zones, probably through compression or other acceleration processes. So why does all this deep diving into solar particle acceleration matter? Well, the close-up discoveries by Parker's solar probe are having a massive impact. First, improving space weather forecasting. As we discussed, CEPs can be bad news for our technology. They can damage satellites, mess with GPS and communication systems, and they're a serious radiation hazard for astronauts. If we can better understand how they're accelerated and how they travel through space, we can build more accurate space weather forecasts and early warning systems. Think of it like getting better hurricane forecasts, but for storms from the sun. Second, understanding fundamental plasma physics. The sun's corona is basically a giant natural laboratory for studying plasma, the fourth state of matter. Under extreme conditions you just can't replicate on Earth. Parker Solar Probe's findings on how particles get accelerated by things like magnetic reconnection and shocks aren't just relevant to our sun. These are fundamental processes that happen all over the universe, in distant stars, nebulae, and around black holes. So, what we learn about our sun helps us understand the cosmos. And third, protecting future exploration missions. As humanity sets its sights on going back to the moon, to Mars, and even further, knowing how to predict and mitigate the risks from SEP events will be absolutely critical for keeping astronauts safe and ensuring missions succeed. Parker's Solar Probe isn't done yet. Not by a long shot. It's continuing its daring mission, and with each orbit, it gets closer to the sun, promising even more detailed and groundbreaking data. The spacecraft is set to remain in its optimal orbit, making these incredible close approaches roughly every 3 months. For the rest of its primary mission, scientists are buzzing with anticipation, expecting ongoing observations to keep peeling back the layers of our star's secrets, further refining our models of how these energetic particles are born and how they journey through the solar system. The Parker Solar Probe mission is truly a marvel of human ingenuity. It's pushing the very limits of exploration, bravely venturing where no probe has gone before, all to unlock the fundamental secrets of the star that sustains us. The insights we're gaining are not just academic. They are vital for our technological society and our future as space explorers. It's a beautiful reminder that there's always more to learn, especially about the fiery heart of our cosmic neighborhood. That's all the time we have for today on G Fun Facts Online. Join us next time as we continue to explore the amazing universe around us. Stay curious, everyone.